In this lesson, we're going to put all of your statistics skills together and look at how to solve problems involving what you know about normal distribution. In the first example, we have a company producing light bulbs. They've figured out that the average life of their light bulbs is going to be 900 hours, and they've also calculated the standard deviation. Now, if the data is normally distributed, the first thing that you want to do always is draw yourself a bell curve. Not only is the bell curve a visual way to see and to check what's happening, but in some cases such as this one, we're looking for the percent of bulbs that are expected to last between 850 and 900 hours. If we start with the mean in the middle, add the standard deviation, add the standard deviation, add the standard deviation, and then on the left subtract the standard deviation, subtract the standard deviation, and so on, we can see that 850 and 900 happen to lie both on the mean and one standard deviation respectively. That means we don't need to spend time calculating the z-score. We can look at our formula sheet and see that 34% of the data falls within this range. So that is going to be our answer. 34% of the light bulbs are expected to last that length of time. Now, notice the difference between the wording on this one and the wording on the next one. This one's asking for the percent of bulbs. This one's asking for how many bulbs. They want to know the number. Remember in the question, it tells us that we have produced 15,000 bulbs. So I want to figure out between 850 and 900 hours, how many bulbs from the production line are expected to last. So I'm looking for what is 34%, we got that number from up here, of the 15,000. Now we know from previous years of study, when we're finding percent of a number, you're going to change your percent to a decimal and you're going to multiply by the total amount. And that means we would be expected to have 5,100 of our bulbs last that length of time. In our next question, we're looking at bottles of juice that contain a certain volume. The bottles are normally distributed, so we're going to draw a bell curve, given the mean and the standard deviation that were provided. So when I set this up, I can see that I'm going to put my mean in the middle. I'm going to go 1, 2, 3 standard deviations above, and 1, 2, 3 standard deviations below. I'm now looking for the percent of bottles that I would expect to have a volume between these two volumes. So we can see on here, 995 is going to be about a third of the way over here, and 1004 is going to be about a third of the way over here between these two values. Because I do not lie right on the standard deviation, we know that we need to calculate a z-score. My first z-score is going to round to negative 1.67. Now it's really important that you round properly. If you don't, you're going to get the wrong percentage. So follow your rounding rules, make sure you round up in this case. So that's over here, and then take a look. If this is the mean, this is 1 standard deviation below, this is 2 standard deviations below. And because we are a third of the way from this value, we are 2/3 from this value. So there's lots of ways you can check to make sure that this is making sense. My second z-score over here is going to be 1.33, and again, it's 1 1/3 standard deviations above the mean. We're going to use our z-score table and we're going to look up those percentages that correspond. Now remember, the z-score table gives you the percent of data to the left. So if I take my first z-score, I have 4.75% of the data to the left of that number. If I take my second z-score, I have 90.82% of the data to the left. So that's all the way to the end. I don't want all the way to the end. So what I can do just to get the data values between here is I can take this whole amount, remove the section we don't want to include because we're only looking for the shaded region, and that will give us the percent of bottles between those values. All right, so when we subtract those two values, we end up with 86.07%. And then go back to your diagram and check. We know that within 1 standard deviation of the mean, this is 68% of our data. Now, we end up with the largest 2/3 of this section. We end up with the largest 1/3 of this section. We can see that 1/3 here is a lot greater area than 1/3 on this end. So that number is reasonable given our diagram. All right, I want you to pause the video and you try to do this last one now. So in a shipment of 576 bottles, how many bottles would we expect to have a volume less than 996 milliliters? Because 996 does not fall right on 1, 2, or 3 standard deviations, I know I'm going to have to calculate the z-score. So 996 is between 994 and 997. It's going to be about there. And when I calculate my z-score, I'm always going back to what I know about z-scores. So my z-score needs to be between -1 and -2, about a third of the way over, which it is. So that's good. Now we're going to use our z-score table, and we're going to look up the percentage of the data to the left of that score. And we can see that that's this area here, which is the shaded region on our graph that we're looking for. But again, you have to watch the wording in the question. This particular question doesn't want that percent. It wants to know how many bottles. And so we're going to take that percent of our total shipment of bottles. It tells us how many bottles we have. And when we calculate that, this is the number we end up with. Now, when it comes to rounding, because I want to be less than that, this is the number of bottles we would expect to have less than that. Because I want to be less than, I'm going to round that down. Our final example is a little bit different. In this example, we're given the average distance and the standard deviation, at which point most running shoes lose their shock absorption. Zach, who's an elite runner, wants to replace his shoes after 25% of their natural life, so he doesn't end up with foot and leg problems. You're trying to figure out at what distance should he replace his shoes. Now remember, along the x-axis, these represent our distances. This is 640 kilometers, and the standard deviation is 160 kilometers. That's the amount we're adding or subtracting every time. So we are looking for what is the value along here he needs to replace his shoes at. Now, how did I know that this is the point I'm looking for? We're trying to replace after 25%. So go back to the percentages that we know if the data is normally distributed. I know in this point, I have 2.5% of my data here. So if we were to replace here, that's only 2.5% of their natural life. I know that this is another 13.5%. So 13.5 plus 2.5, this is 16% of my data represented in these three sections here. I also know this is 34%. I'm not at 50% yet, so I'm going to be somewhere between this point and this point. So I just estimated I'm going to be looking for approximately what that value is. Now, in order to do so, we only have one formula. We're looking for the x value, so we're going to start with that z-score formula. Okay, so it's the x that we are looking for. We know the mean and we know the standard deviation. We can only have one variable in this formula to be able to solve it. So I'm looking for x, which means I have to know what the z-score is. We know already that on the normal distribution curve, if the mean is 0, we're going to have -1, -2, -3. I can see that my z-score is going to be somewhere between 0 and -1, but I need to get that exact value. So in order to do that, think about what we know. We know that to the left of that point that we're looking for is 25% of our bell curve. As a decimal, that is that 0.2500. I need to go back to my z-score table and look through the middle section to find the z-score most closely corresponding to that percentage. Okay, so when we go through the z-score table, and again, we know it needs to be between 0 and -1. So I'm going to be looking somewhere down in this region. And we can see that these are the two values surrounding 0.2500. I need to get the closer one. So if you're not sure, we can clearly see that this is going to be 14 hundredths of a percentage over, and this is going to be under. But if you can't exactly tell which is closer, take the value we're going for and find the difference between each of those ones. Ignore the sign. This just tells us if we're under or if we're over, or vice versa. So in this case, we can see that we're 17 hundredths of a percentage point away from our target. Here we're 14 hundredths of a percentage point away from our target. So this is the closer one. So the z-score that corresponds to this value is going to be -0.67. I'm going to substitute that z-score into my formula, and then algebraically we're going to solve for x. So the first thing I need to do is remove this denominator. Right now I'm dividing by 160, so I'm going to multiply by 160 to get that off the bottom. And then I'm going to do the same thing on my other side to keep it balanced. So I want you to pause the video, go through, and see if you can algebraically get that value of x. All right, this is the value we end up with for x. I want to replace the shoes at 25%. If I go a little bit over, then we're a little bit over that 25%. So that's why I rounded down in this case. I'm going to now show you how to do it on the graphing calculator, so stay tuned if you want to see that, but be aware the expectation for this course is that you can go through like this manually and show how that value is derived. Similar to what we did in the previous lesson, we're going to take the inverse norm and we're going to get to that distribution menu on the calculator by going second function vars, and number 3 is going to give us this. If we know the area of the bell curve that's shaded and we're looking for that particular x value, this is when we can use that function. So we're going to have to enter these data values. So in our case, 25, we're looking for the value of x when we have 25% of the curve shaded, given the mean and standard deviation provided. On the TI-83 calculator, we're going to go into second function vars to get that distribution menu. We can see number 3 is the inverse norm. So the bracket pops up. We're going to enter 0.25. So we're looking for the value of x, comma, given 25% of the bell curve, with a mean of 640 in our running shoe example, comma, and a standard deviation of 160. We're going to close the bracket. And again, it's going to be around that 532 kilometers that we're going to replace our shoes. And on the TI-84 calculator, we're going to start the same way with that second function vars. We're going to go to number 3, and you can see the differences here that they're going to kind of prompt you. So we're looking for the x value given 25% of our curve. Now they've put in here the mean of 0, standard deviation of 1, but in our case, we're going to substitute in our mean is 640, our standard deviation is 160, and then we're going to go enter, 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 and there's our value.